Okay, so today we're going to kick off KNN. It's actually fairly short of a section. It's a pretty simple algorithm, so I'll talk about that. But before we start with KNN, addressing a couple questions. So first of all, I didn't go very in-depth into this because I feel like with logistic regression, it was kind of like overshadowed by like classification metrics in general. So this was actually in we have this in, I think, section 25 lessons. But the question was, what exactly is the decision function for that we're using as part of our ROC curve? So just for a little bit of context again, this was the iris data set, I believe. So this was the iris data set. And for ROC curves, you need to take a look and see if we're moving the threshold, how does true positive and false positive rate change, what that trade-off is. And that's pretty much what an ROC curve is showing you. And for multi-class, because ROC curves use this like idea of true positives and false positives, when you have multi-class, what exactly is the positive negative case? So because of that, when you're dealing with multi-class and when you're dealing with any metric that has positive negative, especially with precision and recall, you're doing a one versus all approach for each class. So in this case, which is why you sort of see here that in our classification report for like precision of each class, you have a precision for each class. And that just for each, I keep saying that over and over again, but for each class, you are taking that class to be the positive and the other two classes to be the negative case. And that's how you're calculating how many points belong in your false positive and your false negative buckets. So with ROC curve, again, because it is looking at true positive and false positive rates, you need to have one curve per class. So for this, the way that you decide on your ROC curve is you have to use the decision function. And what the decision function is, if we actually pull up, this is the documentation for logistic regression. The decision function for logistic regression basically shows you, it outputs the confidence scores for the samples. To be honest, I'm not even sure what exactly the decision function is, like how it's calculated, but it says it's a signed distance of the sample to the hyperplane. So looks like it is how confidently are you classifying something is some measure of you can sort of think of it as abstractly as how far from the boundary, your decision boundary, a point is. And so you can sort of see here, these are your decision scores per each test sample. And you can sort of see that these are three classes. I'm guessing for this, it'll be 0, 1, and 2. And these scores actually add up to 0. So basically, if you add up these, it's sort of like a score for how likely it's going to be in each class. So you can use that. And with 0 being your 0.5, I believe that's how they do it. 0 being your 0.5 decision boundary, you can shift that back and forth to basically create your ROC curves. I don't know if that helps. But yeah, that is what that decision function is doing, is basically, I think it does work slightly differently for each algorithm that we will be talking about later. But in this case, it gives you like some sort of score, or in this case, like a distance from the point to the imaginary like decision boundary that your model has created.
And it's just doing that for different thresholds?
I believe so. So let's see. The way the ROC curve is using the scores, it seems like, yeah, it's calculating an AUC for each score, I believe. Yeah. I'm not 100% certain what exactly the calculation is and how it's going on here, but it'll be I imagine it's pretty similar to a binary case. But yeah, I think they are basically taking these scores, and these scores are like the scores for a threshold at 0.5. And I guess if you like shift your threshold between like a scale of 0 and 1, how would these scores change? I think it's something to do with that. But abstractly, that's sort of what's going on and how that creates your ROC curve. Exactly what's going on, I'm not sure if that's exactly how they're calculating it, but conceptually, that's what is happening.
And your decision function is taking your test data, and that's because your ROC curve uses the test data as well. Is that why?
Mm-hmm. Yeah, you can actually create ROC curves for either your train or test data. In this case, because I believe our train function, not perfect, but yeah, you can create ROC curves for either your train or your test. So if you did this on your X train, I believe you can actually get, yeah, you'll get scores for each training sample. And then, yeah, for X test, it's in the same way that you feed it in your test model to give you a prediction. This just gives you the scores that go behind the prediction. That makes sense. Since we're talking about this, something else that might be helpful for you all to know is for logistic regression and a couple other probabilistic models. So the one that we're talking about today doesn't have this, but here you actually see that you have predict probability as one of the methods you can use here. So while you have dot predict, and let me just use this as an example. So here we're doing dot predict on your on X test, and these variables names should change, but just to show what I mean here, predict X test tells you like what class it should be classified as. But if you're curious about the probabilities of like, it belonging in what class, and that is also related to those scores that you saw earlier, you can use predict proba X, and let's see what that will give us. Predict. These will basically give you probabilities that should add up to 1, or I guess maybe not, but basically the probability that something belongs in each class. Yeah, it does add up. It should add up to 1. Let me see. Yeah, because this is 1. Yeah, it does add up to 1. So this is basically the probability of each data point belonging in class 0, 1, or 2. Might be helpful for you if you want to like adjust your thresholds. This is what these are the probabilities that you would utilize. And also could be interesting to just see like as like a post-modeling EDA what your probabilities are looking like if you wanted to like do an extra evaluation on your model. But yeah, just to set context, I guess before I talk about setting the context for logistic regression specifically, any other questions regarding this stuff? All right, so just to set the context for like logistic regression and how that fits in with all of our other models, it is slightly different because logistic regression is the only one that actually has assumptions to deal with. So with logistic regression, we have a very similar modeling process as we did with linear regression. So we have to like, account for linearity between log odds and each feature. You have to account for multicollinearity. So yeah, you have to deal with all of those assumptions. But for most of the algorithms we'll be talking about today on onwards, we actually don't have to deal with assumptions. This, similar to linear regression, a lot of the adjustments you'll be making are with regards to the feature set, like you're editing, the X-trained data that you're feeding into your model. But for a lot of the upcoming models, instead of adjusting your feature set, you will still be adjusting your feature set depending on the model, but not as in-depth. Most of the adjustments will be actually made to the model. And we'll get, I think with, not tomorrow's, but with Thursday's example, today's as well, but Thursday's you'll see a more comprehensive example of like a model that can be adjusted a lot. But yeah, we'll talk about that later. Any questions to close off this for now, just before I move on?
Can I just ask a quick clarifier on the constant you add for regularization? So I know it's inverse related, so that means if it's set at 1, which is like what its default is, there is no regularization, right?
That's right.
But then the bigger the number that you put there, the more it regularizes.
Yep, that's right. So Sometimes they say, yeah, the default is 1, and it is usually, it's basically 1 over C will be your regularization. So yeah, you're exactly right. Your bigger number would have less regularization. Cool. Before KNN, I guess this kind of segues into KNN. We got a question of like, what are you predicting with KNN? So KNN is actually, I like to think of KNN as an application of the nearest neighbors concept. And we'll get into that later on as I talk about how the model works. But there's this idea of nearest neighbors when it comes to data. And nearest neighbors you can sort of think about as like, all right, if this data point is in X location, how similar is it to the data points around it? And so with that, with the KNN classifier being an application of the nearest neighbors concept, what are we predicting here? In this case, very similar to logistic regression, you get to choose which column you will be predicting. And I'll be showing an example. I'll be going through an example when we talk about the algorithm, but basically same setup as we've done with logistic regression, similar setup as we did with linear regression. You basically have a target that you're trying to predict. I hope that answers that question. All right. So to begin, we'll be talking about k-nearest neighbors today. And with k-nearest neighbors, what it's built off of is basically distance, because how near something is, we compute that using distance. And we'll be talking about distance metrics. There are a lot more distance metrics than just these, and we will actually come across them as we move through the course. But to start, k-nearest neighbors most commonly uses these distances, and we'll talk about them later on. And then we'll get into the algorithm, how k-nearest neighbors uses these distance metrics to do classification. And then I'll also walk through implementation examples. As a really quick primer, this might be something that you come across in like more technical reading, the idea of what a parametric model is. So parametric models are actually the models that we've talked about so far. Parametric models are linear regression is a parametric model, and logistic regression is also a parametric model. And a parametric model is basically a model that makes certain assumptions of your underlying data. I think it says that right here. Parametric models make some assumptions about your underlying data distribution. So because of that, you had the assumptions that, your target and your variables have to be linearly related to each other, no multicollinearity. For linear regression, you had the distribution of your residuals, stuff like that. These are all things that need to be in place for your model to work the way it's supposed to. So non-parametric models, which is pretty much, I think, every other model that we will be talking about this week, are non-parametric models. And so these non-parametric models, we don't have these assumptions, which is one big reason why you don't have to make very many edits to your feature set, to your training data before you plug it into the model. So non-parametric models, of which KNN is an example, allow us to apply the models to data that are not normally distributed. If some of your assumptions of your data isn't met, you can use non-parametric models. So for example, if you were given a classification problem, and as of yesterday, you didn't know anything about KNN, and you were trying to fit your logistic regression, but you still didn't get any good, really good results, and you didn't fulfill your assumptions, you can try non-parametric models like KNN. Tomorrow we'll be talking about a Bayesian model, and we'll be talking about tree models as well. So just as I guess, semantics, with semantics, you always say that your models are parametric, not our data, which is interesting. But it's more in the sense that your models assume that your data is parametric, have some specific sort of distribution. So that's more of like a lingo thing to just be aware of. Questions about this? All right, so let's get into distance metrics. I'll be talking about 3 main ones. They're actually very, very similar, and some might look kind of familiar. But we'll talk about distance metrics as a way to measure differences between your data points. So let's say you have two data points in space, this corner and this corner. The first distance metric, which is actually the simplest one, is known as Manhattan distance. And it's called Manhattan distance because, Manhattan's sort of like a grid. And Manhattan distance is basically the sum of the absolute values of the Cartesian coordinates. So basically, with Manhattan distance, if you had like a point here and a point here in just 2 dimensions, all you have to do is measure, all right, how far did it move in this direction, and how far did it move in this direction? And that would be your Manhattan distance. So just as an example, we have point A being 2, 4, point B being -1 and 5. And you can sort of imagine this being 2 features that you're using to predict. Your Manhattan distance is basically the sum of the difference between 2 and -1 and 4 and 5. So we'll run this in a little bit, but I expect this to come out to be a Manhattan distance of 4, because in the first dimension, you're moving 3 units, and in the second dimension, you're just moving 1 unit. So this is just a for loop that will sum up the difference between each coordinate, and Manhattan distance is 4. Questions about this? Pros of this one, it's pretty fast to compute. You don't have to deal with like advanced math. It's literally just summing numbers together. And this is one way to compute the distance between your data points. So if you had like 10 columns, you would just repeat this process in 10 dimensions. All right, well, the next distance metric is Euclidean distance. The formula might look kind of familiar, hopefully to some of you, but Euclidean distance is also known as the shortest distance between 2 points, and is the most commonly used distance metric. To calculate it, it looks like this. You're taking the root of the difference between each coordinate, which is actually Pythagoras' theorem. Pythagoras' theorem uses Euclidean distance. If you want to find the length of your hypotenuse in a right-angled triangle, it is this same formula. So Euclidean distance is sort of like finding the length of this green line here. So visually, that's what it looks like. And the formula, no matter how many dimensions you have, the formula is just summing up the difference squared for each dimension. So between any 2 points, you can compute this Euclidean distance. And if you have, again, in this like expanded formula, if you have many, many dimensions, you would just repeat this for every dimension, and it will always be squared, and it will always be a square root of the entire sum. All right, so here's another Python function that does this. Euclidean distance between the 2 points is 3.16. It does make sense that the Euclidean distance is smaller than Manhattan distance, because instead of going like that and like that, you're just going straight across there. Like, it just makes sense that it's shorter. And yeah, Pythagoras' theorem is how I like to remember Euclidean distance. As a side note, I have these functions here, but they all have built-in methods for these functions. I believe it's in, I want to say it's in SciPy distance. Yeah, so there's like a spatial distance that you can get. Here you can see you have, I wonder where Manhattan distance is, but you do have Euclidean distance, you have squared Euclidean distance here. You have a bunch of other different ones. Oh, here, city block distance is Manhattan distance. And these are all sorts of other distance metrics they can also compute, but I will only be talking about the 3 main ones. So we have that one, Euclidean, and the one I'm about to talk about is Minkowski distance. So if you ever need to compute the distance for something, you can use these. So back to this. Lastly, we have Minkowski distance, which looks very, very similar to the formula for Euclidean distance. So Minkowski distance is actually a generalized form of Euclidean distance. If that doesn't make sense, basically you can plug numbers into Minkowski distance to get the formula for Euclidean distance. So you can sort of think of Euclidean is a subset of Minkowski distance. It has this formula, the main difference being that whatever power you're raising the difference to, you can take the root of whatever that is. So with Minkowski distance, you can actually take the cube of the distances between points, and then you would cube root it. And you can also do this with higher powers. with Euclidean distance, it's only for the power of 2. So Euclidean distance is Minkowski distance, but only raised n rooted by a power of 2. So yeah, sometimes, and you might see this in more technical ratings, the Manhattan distance will take on the notation of L1 norm. So you can find like the L1 norm between 2 points, and Euclidean distance will take on L2 norm. And so this should remind you of Pythagoras' theorem. Questions about these distance metrics so far?
Excuse me, in the list of distance computation by SciPy, there was a Euclidean and a S-Euclidean. What is the difference between these two?
Yeah, so this, let's see, I actually haven't seen, I have not like gone into each of these, but I'm guessing, so this would be a squared Euclidean distance. So I guess this one you don't do the square root with Euclidean distance. And then standardized, I'm not exactly sure what standardized Euclidean distance mean. I am not too sure. I wonder if they say it in their documentation. Yeah, I'm not exactly sure exactly what that standardization means, but it could be something that, yeah, it's probably just Euclidean distance with some transformation. I think a quick Google search can help you figure that out. But yeah, that was a good like good thing to point out. Yeah, there are all these other distance metrics. I personally haven't used any of the other Euclidean distances. I mainly just try those 3. Other ones that I've used before are cosine. Cosine we'll actually talk about next phase, if not sooner. Jacquard distance is one that is also used in recommendation engines sometimes. And that is all I currently can pick out from this list. But yeah, basically a lot of ways to compute the distance between points. And for the most part, in lower dimensions, typically in lower dimensions, you get very similar results. But once you have more dimensions, different distance metrics might give you like a different order in like which points are closest versus nearest from the point that you're looking at. All right, before I get into the algorithm, any other questions? Cool. All right, so KNN, as I mentioned, is one of the simpler ones. I feel like conceptually it's easier to understand, and so I'll just talk through how it works later. It is non-parametric, so again, you're not making any assumptions for this. You can run KNN on any sort of, on any data pretty much. And it's also a lazy algorithm. We'll talk about lazy in a little bit. KNN can also be used for both regression and classification. We'll talk about the classification case today, but I'll send out a reading on how KNN can work for regression as well. So again, I said non-parametric because it doesn't make any assumptions, and it's lazy because it doesn't actually learn a discriminative function. So it's not really learning patterns within your training data. Like with logistic regression, it was trying to see like, okay, what is the relationship between my log odds and my different features? Linear regression as well. What is the relationship between my features and my target? Instead, you're sort of memorizing the training data set. What KNN is doing is it's trying to put in space where all the training data is. It's just memorizing where everything is, and it's going to be computing distances over and over again. So the algorithm ascribes class membership based on the closest k neighbors to the testing observation concerned. So let's just say that your squares and triangles are different points in your training data. So with your squares and your triangles being points in your training data, and you have this green circle here, we're like, all right, we're going to classify this point based on the points closest to it. So that's the whole idea of how KNN works. We're going to classify this green point based on the points closest to it. What you're tuning here, why it's k nearest neighbors, not like 1 or 2 or 3 nearest neighbors, is because you get to decide how many of its neighbors you want to consider in making this classification. So just from this picture, you can see that, all right, let's say I just want to consider 1 nearest neighbor. The nearest neighbor in this 2D example, the nearest neighbor to this green circle is this blue square, which is class 1. And because this is the closest, you can sort of make the assumption that, all right, well, this green circle is very, very similar to this blue square, therefore it's class 1. So that's like the easiest example to think about, I think. If you're using a different number of neighbors, your result can change. So in this example, you sort of see that the next two nearest neighbors are actually, and let me circle them for you. The next two nearest neighbors are, so you have this one first. Next, you have these two red triangles. So with these two red triangles, your classification changes because it just looks at your three nearest neighbors saying, all right, well, I have two that are class 2 and one that is class 1. Therefore, I'm going to classify this as class 2. Later on, what we'll see is you can actually adjust this a little bit such that if a point is closer, it'll be weighted higher. And if it's further away, you'll weight it lower, which makes sense. You want to consider your closest neighbors a little bit more than your neighbors that are a little further out. And we will talk about how we can adjust that a little bit. So as mentioned, and let me clear this for now. Oh, any questions about this concept before I move on? Cool. So similarity does depend on the distance of observations from each other, which can be calculated using any of the distance metrics mentioned above, can be calculated using any distance metric that exists in SciPy, actually. The most commonly used one is Euclidean, and which distance metric you use, as well as the value of k, will affect the performance of your model. And so the decision boundaries will change accordingly to different values of k. So that's literally all there is to KNN classification. If you have a test data point, you're going to look at that test data point, find out what is close to that test data point, and based on the nearest neighbors, decide on your classification, just like that. So with implementing KNN, we're going to use the same iris data set that we use for logistic regression real quick. So let me just load our X and Y. We have that loaded, and in our X, we have, yeah, I think here we only have 4 columns. I believe it was sepal and petal, length, and width for each of them. So first, as we know, we're going to import from Scikit-Learn neighbors the k nearest neighbors classifier. Next, we're going to instantiate it. And in the instantiation step, very similar to what we were doing with ridge and lasso and with logistic regression, in the instantiation step is where you can define your hyperparameters. So here, your estimator is this, and you're making an instance of this. And here we can specify how many neighbors you want to look at. And let me actually pull up the documentation here. So let me just move this out of the way real quick. Right. So by default, the number of neighbors it considers is 5. As I mentioned earlier, you can tell it what weights to consider. So you can do uniform weights. So basically, in this example, even though these 2 points are further away, it will be considered with the same weight as this point. You can also do it, let's see, by distance. So you're going to weight points by the inverse of their distances. So as I mentioned, closer neighbors of a query point will have a greater influence than neighbors further away. And you might want to implement that as well. And this is just another function that will accept different distances if you decide to do that. So back to this. Oh, I guess really quickly, with your metric that you can tune, the default is Minkowski, but you can have it compute any of the distance metrics. I believe you can actually feed it in the SciPy distance object, and it will compute whatever distance you give it. So back to our notebook. After instantiating a classifier, and let's just try one neighbor to begin with. After that is instantiated, again, we can just fit our model. This is a really simple example. I haven't done train test split, but I have another example right below this that does. And then really quickly, we can make predictions. As I mentioned before with that NumPy reshape, this is kind of what I'm doing here. You can see that there's 2 layers of square brackets here. And I know that I only have 4 columns, so this is just 4 random numbers that I've plugged in here just to see what my values would predict. And you can see here, running this, have a prediction of 2. I can also do this on multiple points. I have a prediction of 2 and 1. So something that's pretty cool, we can sort of see differences in your classification based on your number of neighbors. So just really quickly, I'm going to adjust my n neighbors to 5. And earlier here, it was 1. So just by changing this, and I'm repeating the same steps on these 2 data points, my predictions change from 2, 1 to 1, 1. Of course, I haven't gotten into evaluation yet. I haven't gotten to see like what the right one is, but that's something that you can tune for, and basically tells you that the number of neighbors you consider can change your classification result. Questions about any of these processes before I move on? All right, so just to put it all together, and I just put the code back here again. What I'm doing here, loading in the data set, storing X and Y, doing my train test split. What I'm also doing here is I'm scaling my data. And I'll talk about scaling after this. So scaling my data, fitting the scalar on X train, transforming it on both. And I'm just going to train a classifier to predict with one nearest neighbor and get our predictions on the test set. From here, what I'm going to do is I'm going to plot my confusion matrices and my classification report. For any classification model, I think it's a bare minimum to have your confusion matrix and your classification report, because those just tell you pretty much anything you need to know about your classification results. So that's done. With our train confusion matrix, you can see that it actually classified perfectly on our training data. And oh, nice, perfectly on our testing data as well. And just really quickly, because these were all perfect scores, you expect your classification report to also have perfect scores, which is great. So something to think about, let's go back to talking about why we're scaling our data. So because this is a distance-based classifier, having your features on different scales can really affect your result. It's not always the case that you want to scale everything, because sometimes you do want to say like, all right, well, these numbers are higher. Maybe I do want to consider these more. Like in this example, I may or may not want to scale because I know that for this data set, everything I believe is measured in like millimeters or inches or something. And they're all actually already measured in the same units. And maybe I can make a decision whether I want to scale or not. So when you scale, that means that like the differences in your feature set will have sort of the same effect on your distance, if that makes sense. If you imagine you have like one feature that's like measured in thousands and one feature that's measured in like single digits, like a change in like 1,000 will add a lot more to your distance, your overall distance, compared to a change in like the one measured in like single digits. I don't know if that makes sense. Basically, if you're to plug in much bigger numbers to like your Y here versus your X, you can blow up your distances. So it's really up to you to think about in context. Do I want all of my features to be around the same scale? What are your features measured in to begin with? And that will sort of determine whether you scale or not. I think if you're working with a data set that one has a lot of dummy variables or has features that you're not too sure about, I think it makes more sense to scale such that no one feature is being overweighted. But with k-nearest neighbors, good to at least think a little critically and think about, all right, if I'm scaling it, what are the implications? Am I going to be taking a somewhat important feature and minimizing its effect, or the other way around? That's things to think about. Just because the scale of your numbers does affect distances greatly. All right, so next we're going to talk about hyperparameter tuning and what value of k is best to use. There are multiple ways to go about this, but really quickly, why don't I test all of the k values between 1 and 40 just to see how my model changes based on that. So what I'm doing here in this function, I'm going to look at each k from 1 to 40. I'm going to be training a model at each time. So I'm basically training 40 models here, each with a different k number. Fit the model and just take a look at what the score is. And the score here, you can actually plug in KNN.score, and score for KNN by default gives you accuracy. So you can see here, score gives you the mean accuracy on your test data. So what I'm going to do here, and because it's a fairly small data set, it's going to run pretty quickly. I'm going to get this array of numbers. So before, remember, we saw that with our neighbors being one neighbor, we get a perfect classification. Let's just see how that changes as we increase or decrease k. So I have all of these values. I'm just going to plot them on a graph. So overall, it seems that, you know, as I increase k, our overall accuracy score just keeps going down. It does fluctuate a little bit on the high end, but typically, I think with a bigger data set, you'll get a smoother looking curve. But this is one method you can use to decide on what your best k value is. Probably for this, I think because even on your test set, you have a perfect classification. Maybe you want to get other data points from elsewhere to just confirm that. But it seems that for this case, I would use probably one neighbor for this model. Perhaps if I want to give it a little bit more leeway, maybe 6 neighbors looks to be good as well. But yeah, these are things that you can test with different data. I believe because this data set is very, very small. I think there's only like, 150 data points. But yeah, the number k in bigger data sets actually does have implications on the bias variance trade-off. So if you don't remember, the bias variance trade-off was, in short, the trade-off between over and underfitting. So typically, the higher your k is, the less you overfit your data. So these diagrams show how the different number of different k values affect your decision boundary. So this is a data set that is fairly well split. Like there's only a little bit of overlap in the middle here, but let me zoom in. You can see that with k being equals to 1, the decision boundary is not as smooth. It's really considering that, all right, these blue points here, the nearest neighbors to that. So because of that, your decision boundary with a lower k tends to usually overfit. As you lax your k, as your k gets bigger and you're considering more data points around it, you kind of account for the overfitting in that way. So typically, smaller k leads to low bias, high variance, higher k leads to high bias and low variance. I don't know if anyone has seen illustrations by this guy, Chris Albin. He does like a series of very simple, good summary illustrations about machine learning. So if you look him up, he has a lot of good illustrations. But yeah, that's pretty much all with KNN. The main things you would tune again are trying different values of k. I would say like in your working groups, maybe different people try different distance metrics to see how that changes your model results. And also the weighting of your distance, whether you want to weight your distance by the inverse of the distance of the points from your test point. I've also linked a couple resources here. These are the Scikit-Learn Documentations. This is that textbook that I've talked about that I said, like, if you are interested in like getting into the weeds of machine learning algorithms, this textbook actually comes with a set of videos, and the videos are linked here. And then a bunch of other readings that you can read about KNN. But cool. Any questions so far? Awesome. Well, this is all I had to share. This is one of the simpler classification algorithms. I will say KNN, if you are interested in recommendation systems and like building recommendation systems, KNN is a good one to learn. We will only formally get into like the idea of recommendation engines in the next phase, but just in case you want to like sort of weigh and figure out which ones you want to focus on, if you're interested in recommendation engines, KNN is a good one to figure out. But cool, tomorrow we'll be getting into Bayesian classification, and so it'll be we bring back some probability concepts from phase 2, and then after that we'll be getting to decision trees. So that's what's coming up. But yeah, any final questions to wrap up?
Excuse me, we have to look for our data in multidimensional form, right? Where exactly is our first position of our unseen data to calculate its distance between other data points?
Yeah, so let me go back to this image. So our training data will be like the red and the blue. And this training data, where it is in space, is defined by all of the X features, right? With your unseen data, you have your X test, and your X test determines where in space that is as well. If that makes sense. So it's basically coordinates. So if we take a look at, not this one, let's use the train and test that was here. So we have our X train, and let's do like a quick iLook of the first 2 data points. Oops. This is not a data frame. Right, so these are our first 2 data points, and these are literally like, you can think of them as, I don't know if that would be helpful, but you can sort of think of them as coordinates as to where they are in space. And with our X test, let's just take a look at 2 as well. These are our data points. So what you're doing is per each test, and actually let's just look at 1. For this, what the algorithm is doing is it's taking this test point, and actually let me give more examples of the train. It's going to compute the distance between this and every other point in your data set to figure out which are the nearest neighbors. And so after it does that, then it says, all right, these are the points with the shortest distance. Let me see what their classes are.
Okay, thank you. Yeah, thank you.
You're welcome.
And then that reminded me of the stats quest. He uses PCA in it, and maybe that's because he's a biologist and it makes more sense to reduce like these random variables. But is that something we would be looking to use that with KNN?
So yeah, PCA is commonly used with KNN. I would say KNN and another one called SVM, which we'll talk about next week. So KNN, you can sort of imagine in very high dimensions, it is it'll just take a long time to compute distances between each test point and every other test point. Because of that, it's very, very computationally expensive. PCA, which is something that unfortunately we only talk about at the start of phase 4. I will do a little quick like summary of it at one of our office hours in phase 3, just so like if any of you want to use it, you can. But the idea of PCA is it reduces the dimensionality of your data. So let's say you have like 500 columns. You can use PCA to reduce it from 500 to 50 columns. Of course, the way you interpret each of these 50 columns, each column is going to be some linear combination of all 500 columns. So it becomes a lot harder to interpret, but very useful for making algorithms run faster. So yeah, you can definitely take a look at PCA for running KNN, because it does make it a little quicker. KNN is one of the slower models just because, again, it's not really learning patterns in your data. It literally is computing distance between your point and every other point. But yeah, I'll definitely bring back PCA and talk about it.
I think he was using it as like feature selection too, to just like narrow it down to the top 2.
Yeah, that's a really good, that makes a lot of sense as well, because in PCA, you can imagine that your new features are created by, each new feature is a combination of your original features, and you can actually extract the weights, like which feature of your original features is being used more in this set of new features, and you can sort of use that to select your features. And that makes a lot of sense as well. But cool, yeah, we'll talk about PCA in depth in the beginning of phase 4, but I will talk about it during one of our office hours because some of you might want to use it. Cool. Any other questions? All right, if there is nothing else, I will see you all tomorrow to talk about Bayesian classification. And as usual, any questions that you come up with along the way, just let me know. All right, then, well, have a good rest of your day, everybody. Hope this classification stuff isn't driving you all crazy. Bye.
Bye, thank you.